Welcome everyone to Unit 1, Lesson 14 of Precalculus, which is all about function model constructions and their applications. So first and foremost, we're going to talk about a vocab word that we're going to focus on for the beginning of this lesson, which is called regression. And regression is the way we estimate a relationship between a dependent and independent variable. It's essentially we're taking the data we have, building a model off of it, and using that model to make predictions about data within or outside of our data set. So let's talk about some different types of regression. So the main types that you're going to see throughout this course are your linear, your quadratic, your cubic, not really quartic, but it's there. Those are all polynomial based, so you'll see those in Unit 1. Exponential, logarithmic, and logistic are all exponential based. We'll see those in Unit 2. And then you have your sine or other trig functions that you'll see in our trig unit in Unit 3. So what do I mean by regression of this type? I mean that our data forms these general shapes. And to remind you what those general shapes look like, our lines, our linears, or anything that looks like a line. It could be increasing, decreasing, it doesn't matter as long as your data looks like it has a consistent change within its data. Quadratic, you have that nice parabola shape. Cubic, you have like your up and down motion. It doesn't have to be as drastic as this, remember, as long as it's slowing down and then speeding up afterwards, you get your cubic. Your quartics are like your W-shaped functions. Again, those are generalizations. They could be flipped for decreasing versions or so on and so forth. Those are all of your polynomial base. These are all polynomials. The other ones we're not really going to see right now, but it's important to talk about them so you have an idea of what we're looking for and what we're comparing against. Exponential is where you start off small and then get really big really quickly. Logarithmic is kind of the opposite. It grows really fast to begin with and then still grows, but not as much. Logistic is weird. It's where you don't grow very much, grow a lot, and then don't grow very much again. A little weird. And then your sine is where you're repeating phenomena. So anything that repeats periodically, like the weather or the position of the sun in the sky and stuff like that, anything that happens on a periodic basis is going to use a sine regression. So what I have here for us is a regression style question. We're going to create a function based off of this data, and we're going to use that function to predict some behavior. So first of all, we have Amazon's net worth in billions for certain years. For us, and to make life easy for us, what we're going to do is we're going to call this year 0 and then name all of the years based off of this. So 4 years later, this is another 4 years. This is 6 years, so that would be 14. This would be 7 years, so that would be 21. This would be 3 years, so that would be 24. And this is 2 more years, so this would be 26. Now, we can check to see if I did my math right by going to a calculator. Let's turn that on. And we can do 2020, take away 1994, and we do get 26. So instead of using these numbers for our x's, we're going to use these numbers here for our x's. And we can use these as is for y. We don't really need to change them or modify them in any specific way to help us with our predictions. Now, the reason we're going to do this is because we really don't care about Amazon's net worth in the year 1990 or anything before 1994. So it's okay for us to say, you know what, that's going to be our starting point. We're going to make that our reference point of 0. So what I'm going to do is I'm going to try to quickly plot some of these points. We got 0, 0. So we have this behavior of increasing, decreasing, and then increasing again. So when we talk about regression, we have to think about what model would be appropriate. And since we have that motion of increasing, decreasing, and increasing again, it's probably going to be cubic. But there are ways for us to tell. And how we're going to tell is we're going to try to use our calculator to kind of help us out. Plotting the points definitely does give us an idea of what we should be using. So we are thinking cubic. I'm going to put a little question mark there. So what we're going to do is we're going to go to mode first of all, and we want to go down until we get to stat diagnostics. And we want to turn our stat diagnostics on. What this is going to do is anytime that we do run any statistics, it's going to give us more data than it would have otherwise. And for us, it's going to tell us how accurate our regressions are. So since we're dealing with regressions, and regressions is statistics, we want to go to stat. So we're going to hit the stat button, which is to right from alpha. And we're going to make some lists. So we're going to hit edit, and we're going to make list 1 our x's and our list 2 our y's. So I'll see you back here when I'm done. Perfect. And I've put in my list, and I can see that I have the same number in list 1 as I do in list 2, which is really, really important. It tells me I didn't miss anything. If my data was consistent in what I missed with. But for us, it just means I don't really need to double check my data right now. So once you have x's in list 1 and y's in list 2, we're going to hit stat again. And this time we're going to go to the calculate page. We're going to hit right, and we have all of these regressions, starting with 4 and working our way down. We have a lot of different types of regressions our calculator can calculate for us. We have linear regression, quadratic regression, cubic, quartic, the ones we talked about before. Another linear regression, if you notice, it's just changing where the y-intercept and where the slope is. We have the natural logarithmic regression, exponential regression, power regression, logistic regression, and then sign regression. So all of those that we talked about before, with a few other ones, but for us, really doesn't matter too much. We are going to mainly look at linear, quadratic, cubic. So let's look at those and see what happens. So I'm going to hit 4, enter. X is my list 1, Y is my list 2. I don't need to put a frequency list. Now here's an important little tidbit, and I'm going to show it to you once. If you have questions about it, you can ask about it in class. But if I hit the variables button, the vars button here, where it says store regression equation, and then I go to my y variables here, function, I can put it in my y1. This means if I want to use this equation to do stuff later, I have it in my y equals screen by default. It's going to take everything it gets from this evaluation, the equation we get from it, and it's going to store it in y1 of the y equals screen. And then I can hit calculate. So it tells us a lot of information. It tells us the equation form, so y equals ax plus b. So a is the slope and b is the y-intercept. So it gives us the slope, it gives us the y-intercept, and it gives us this r and r squared equations. And now these are regression coefficients. These are basically values that tell us how accurate our graph is going to be to the data. We are trying to maximize how well our curve is fitting. So what we want to look for is we want to look at this r squared value, and we want it to be as close to 1 or 100% accurate as possible. As we see here, it's about 74% accurate, so it's not awful, but it's not great. So linear didn't work. Let's try quadratic. So I can go to statistics, calculate, quadratic is number 5. We'll do the same thing, and I'm going to store this equation since the other one wasn't good. I'm going to store it in y1 again, and then calculate. Now the other one was 74% accurate. This one is 94% accurate. So we can see that we have ax squared plus bx plus c. It gives us all those numbers. Great. 94% accurate is pretty darn good. But let's try one more. Let's go to stat. Let's go to calculate. Cubic is 6. All of that is good. We want to store a regression equation in y1, just because if I want to do anything with it, it becomes a lot easier to do so. Enter. And we get all of these numbers, and we get 99.7% accurate. Now that is amazing. That's a pretty good regression. So it is cubic. So what I'm going to do here is I'm going to write yes, yes it is. And then I'm going to write our regression equation. So our regression equation is going to be f of x is equal to, and it gives us the form here of how we're going to write it. So ax cubed plus bx squared plus cx plus d. We're going to write all that down, but we're again going to round everything to the third decimal place. The importance of having it stored in Y1 is that when it performs calculations, it's not using estimations of estimations, which makes our numbers we get from our calculations with this equation more accurate. But if you're asked for a regression equation, round to 3 decimal places. So we have 0.028 x cubed minus 0.6, that's about 0.7, isn't it? 0.7x squared plus 4.708 plus 1.092. So this is a pretty decent regression equation, and sometimes I also, just for myself to compare, especially if I wasn't sure, I would do all my calculations, I would write down all my equations, and I would write down what the r-squared value is, which in this case is 0.997. Pretty darn good. Now, what I can do with this equation, it's not asking it here, is I can actually create a table and figure out what the values of this would be in 2004, for example. What would that look like? So to do that, to actually plug in numbers, we're going to do is we're going to go to table set here, so second table, and we're going to turn our independent to ask. What this does is it allows us to pick the x values we want instead of it just picking the ones for us. Then I can go to a table and we can play with some numbers. So for example, if I want to know what happened in 2000, 6 years after 1994, so I would do 6, enter, and it looks like it should be about $10 billion or $10.1 billion in the year 2000. If I wanted to find what the net worth would be in, let's go with 2014, which would be 20 years after 1994. Well, that's about, and we can scroll on top of it if we're not sure what that says. So that's about $37.9 billion in net worth. That's pretty good. So we're using our function here to estimate values that we didn't have before. Now, why is that important? Well, we can use our function to model the average rate of change from 2008 to 2022. So what we do here is, well, we're not using the years as written, we're using our x values. So we're starting x0 at 1994. So 2008, we've already said, was 14 years after 1994. Then we got 2022, that would be 28 years. So we're going to do 28, take away 14, over. Now, here's where things get a little bit fishy. Most of the time, if you're asked a question like this, I would assume that you wouldn't have the data. But we do have the data for 2008, and it was 2. What does our function tell us happened there? So that was 14. So 14, we're expecting to see 2, and we get 6.2, essentially. I'm going to tell you, since it says use your model to find, that we're going to use the output from our function. We are going to do f of 28 minus f of 14, simply because that's what the question seems to be alluding towards. So how can we do this? Well, we have a couple of different ways we can do it. We can type in 14 and type in 28. 28. And we can write those numbers down and do it this way. So we have 194 point, let's make sure we get that number right. So we're going to go on top of it. 194.968. Just really mess that rounding up. 968, take away. Let's go up on top of the 14, and we get 6.193 all over 14. And then our calculator can do that, so second quit, alpha y equals enter, 19.4.968, take away 6.193 all over 14, and we get about 13.484 as our average rate of change. Now, you might be yelling at me through the screen, or you might not be. What about if we used this equation here? Because we didn't use rounded numbers, essentially, or rounding happened much, much later with the functions in the y equals screen. What if I didn't save that? What if I used our rounded equation instead? You're going to get something that is going to be slightly different, but that's the importance of showing your work. By showing your steps, I can see your thinking, and your thinking is what's important here. And I can see, yep, that looks good. Even if your number is not exactly the same as mine, that your process and your thoughts were the same as mine. All right, so that is regression, and that's why I have our fancy calculator here. Let's move on to proportionality. So we say that two things are directly proportional if when I divide them, I always get a constant value. Or you can think of it as y equals a number times x. Inversely proportional is kind of the opposite of that. Instead of dividing two numbers and getting a constant, I'm multiplying two numbers and getting a constant. Which means that if I write it in terms of one variable, I would have y equals a number divided by x. So the idea behind this is usually you have to find that constant. So let's look at an example below. The force in newtons exerted by a magnet on an object made of iron is inversely proportional to the square of the distance between them in centimeters. So what this means is the force is equal to some constant divided by the square of the distance, so the distance squared. So this is going to be our setup. If a magnet exerts 60 newtons on an object made of iron 2 centimeters away, what would the distance be when the force is 10 newtons? So it's giving us a way to calculate our constant. It gave us 60 newtons on an object 2 centimeters away. So 60 is equal to k divided by 2 squared. Or we can rewrite that as 60 times 2 squared is equal to our constant. We just so happen to have the calculator here, we might as well use it. 60 times 2 squared, which is 4, but sometimes it's not as easy as that. Our constant is equal to 240. So now we can use this setup and a force of 10 newtons to figure out what d would be in this situation. So we have 10 is equal to 240 divided by d squared. So we can rewrite this. 10 times d squared is equal to 240. Or d squared is equal to 24. So d is equal to the square root of 24. Which we can reduce in itself. 24 is made of 4 times 6, so that would be 2 square root of 6 if we wanted to be precise, or like mathematically simplified as we can, or might help us as, realists to try to figure out what that distance would be in centimeters, and that would be about 4.899 centimeters, so about 4.9 centimeters. So that is how you go about those problems, is that you determine which relationship you have. Is it directly or inversely proportional? Figure out the constant, and then use that constant and a piece of information to figure out the last piece. Last thing we're going to talk about is piecewise functions. So we talked about piecewise functions a little bit earlier. Here we're going to actually talk about piecewise functions in an analytical context. So the model here below tracks the amount of snow during a snowstorm, where X is the hours since the snow started, and D is the depth of snow in inches. So what this is telling us is that during 3 intervals of time, the snow was falling in different ways. So it could be modeled using this function for these inputs for this amounts of time. This function, so it was constant at 12 from 4 to 6, and this function would model it from 6 to 9. So the important thing to note is you always really need to look at your subdomains. These are called subdomains, because they tell us which function rule we're using for which input. So when it says find D of 7, D of 7 is no, it's not in that subdomain. It's in this subdomain, so we're going to use this part of the function. D of 7 is equal to 7 plus 3, it's equal to 10. So what that means in context is at 7 hours since the snowstorm started, since the storm started, there's 10 inches of snow. The snow has a depth of 10 inches. There we go. Then it wants to find the average rate of change in the depth of snow from 4 to 5 hours. So the 4 is a little tricky, right? Because I see 4 as a part of this domain and a part of this domain. But the or equal to means that the 4 is going to be part of this one and not part of this one. Because a piecewise function has to follow the rules of functions, your input is only going to appear in one of the subdomains. It cannot appear in multiple. So we're going to use the first equation, or the first rule for 4, and the second rule for 5. So D of 5 is really easy. That is just 12. But D of 4 is a little bit more challenging. Since I've got the calculator here, I'm going to cheat. We're going to do 1/4. Let's do it this way. Let's do, because I want it to look pretty. 1/4. Oh, I missed the 4. 1/4 of 4 squared. No, that's not what I want. That's what I want. 1/4 of 4 squared plus 2 times 4, and we get 12. Well, that's anticlimactic. We have 12 take away 12 over 5 take away 4. We get 0 over 1. So 0 is our average rate of change between 4 and 5 hours. The depth didn't change at all in that time frame, or the average change in depth was 0. So that is it for this lesson, and that is it for Unit 1. So thank you for watching, and I hope to see you in the next unit.